I'm Lynn Bondurant, coming to you from NASA's Lewis Research Center in Cleveland, Ohio. This program, Zero G in Spacesuits, is the third in the series called Life in the Universe. During the series, we're looking at how man has learned to live in space and how he's looking for extraterrestrial life. During this program, we'll see parts of 4 NASA films dealing with weightlessness or zero G and spacesuits. As every science fiction fan knows, before man can venture into space, he needs a protective covering called a spacesuit. The suit protects the space traveler from the vacuum of space and from the harmful rays of the sun. The space garb also furnishes the spaceman with oxygen and heating and cooling systems. During this first film clip, we'll look at the different parts of the spacesuit.
In space and on the surface of the moon, man faces a hostile environment, a near vacuum of heat and cold, of lethal radiation, of bombardment by micrometeoroids. Protection is provided by the spacecraft, but is also needed when man leaves his craft to explore on his own. The overall protective system for a man on the moon could almost be considered a small personal spacecraft. It has 3 main parts. First, a pressure garment assembly, which is the spacesuit itself, complete with inner and outer garments, boots, gloves, and helmet. Second, there is the portable life support system, supplying the spacesuit with oxygen, water for cooling, electrical power, and other communications and life support equipment. It holds enough oxygen for a 4-hour lunar exploration, and it can be replenished in the lunar module. The third major system is the extra 30-minute oxygen supply for emergencies. In addition to providing a safe, livable enclosure, the lunar spacesuit must permit maximum mobility. It is pressurized at 3.85 pounds per square inch when used on the moon's surface. To improve mobility, flexible joints are built into it at the shoulders, elbows, wrists, thighs, knees, and ankles. The pressure gloves are very flexible too. The complete spacesuit is worn by an astronaut when he is outside the spacecraft, either on the moon or in free space. Inside the spacecraft also, during certain critical phases of an Apollo mission, such as launch or docking with the lunar module, the crew must wear their pressure suits. To get into the suit, the astronaut first puts on the liquid cooling garment, like a suit of long underwear. The liquid cooling garment will keep him cool during his work in space. Cold water from the portable life support system flows through the network of tubing next to the man's skin. The water absorbs much of his body's heat and then returns to the backpack for recooling and recirculation. The main part of the spacesuit is a custom-tailored unit covering all the body except head and hands. The hands are covered by pressure gloves, which fit onto the suit. And the pressure helmet locks down tightly upon the neck ring of the suit. The helmet has an airtight feed port for water and food. To increase protection against the sun's glare and heat, a visor assembly fits over the pressure helmet. It has two visors, one to guard against micrometeoroids or accidental impacts, the other to cut glare and block harmful radiation. In free space and on the moon, the entire pressure suit is protected by an outer covering, which shields against micrometeoroids, radiation, and extremes in temperature.
Now let's take a look at a modern spacesuit worn by shuttle astronaut Bob Crippen.
This is astronaut Bob Crippen as he crawls into his upper body and support system. Crippen and John Young will pilot the first shuttle flight.
We're primarily have the suit on board for us in case we get into a problem with our payload bay doors, which are they need to be closed for us to come in and enter. And if we should run into some mechanical difficulties with them, the suit is there for me to go out and try to solve them and close them.
There have been many advances in spacesuit technology since Apollo. The new suits come in two pieces instead of one, so they're easier to put on, and an astronaut can get into the suit without help in a few minutes. With the Apollo gear, it usually took two men more than an hour to get one astronaut dressed.
Like a new pair of shoes or something.
Each new shuttle suit has a microcomputer that offers vital instructions to its wearer. Also, the lightweight fabrics used in these suits give the astronaut greater flexibility. For instance, the thin polyester gloves allow easier handling of small objects. The advanced shuttle spacesuits are being tested in every phase of development, from the drafting board to astronaut checkouts. Now they are preparing for the final test, to perform in space, where the stakes are high.
Spacesuits protect the astronaut from the harsh environment of space, but zero-G or weightlessness is an ever-persistent condition which has to be dealt with. When in a weightless condition, you get a funny feeling in your stomach, much like the one you get when a very fast elevator stops, or like the one you experience when riding a roller coaster. Sometimes astronauts get sick due to weightlessness. Now let's see a few film clips. The first shows what causes weightlessness. The others show how zero-G affects the astronaut and his craft.
Why did I feel weightless up in Skylab? Some people might answer that Skylab was so high as to be beyond the Earth's gravitational pull. This answer is quite wrong. At an average orbital height of 435 kilometers, we were only a few percent further from the center of the Earth than you are today. The gravitational force pulling us toward the Earth's center was only about 12% less than it would have been on the ground. Most of the time, the force of gravity was the only significant external force acting on us. Why then do we use the term zero-G? To understand why, let us examine the motion of a satellite. The little cannon will serve to simplify our explanation, just as it did for Sir Isaac Newton when he first announced the laws of gravitation and motion. If the cannon is fired in the vacuum of space and is also free from the gravitational pull of another body, the cannonball, in compliance with Newton's first law of motion, would travel in a straight line forever at a constant speed. Now, when we introduce a small planet, another of Newton's laws, that of universal gravitation, comes into play. This time, the cannonball, under the influence of gravity, will fall back to the surface of the planet. If we increase the powder charge and fire the cannonball at a greater speed, it may even travel most of the distance around the planet before gravity pulls it back to the surface. Now, if the initial velocity is made precisely correct, the gravitational acceleration toward the center of the planet will produce a curved trajectory which exactly matches the curvature of the planet's surface. The cannonball is now in orbit. The same holds true for orbiting space vehicles, which usually follow an elliptical path around the planet. As with the cannonball, an orbit is achieved when the combination of satellite velocity and a continuous gravitational acceleration toward the planet's center produce a curved trajectory which does not intersect the surface. We may say the satellite and everything in it are continually falling together, since they are merely responding to the force of gravity. Since gravity accelerates satellite astronauts and assorted baggage equally, they have no noticeable acceleration toward or away from each other. Unless some non-gravitational force is acting, such as a muscular push or pull, everything inside the spacecraft remains at relative rest. This explains what you see in orbit. Or for another example, in the Apollo spacecraft coasting toward the moon. Again, gravitation is the only force acting. At a certain point on the way to the moon, the gravitational force of the Earth and the moon nearly balance each other. The crewmen felt no different at this special point because they were always in free fall for the entire trip. As long as gravitation is not opposed by any other force in space, you feel weightless. The sensation we call weight is caused by the pressure of uneven support, by gravity being opposed by the upward force of a chair or the floor. The feeling of weightlessness is similar to what you feel underwater, where your body is evenly supported. But there are important differences because even in neutral buoyancy, you still have many ways to distinguish up and down. In orbit, these minnows could not orient themselves and frequently swam in tight loops during their entire lifetime in Skylab, which was about a month. Even though they had spent their whole life in the water, weightlessness was a new sensation for them, and they responded in this very unusual manner. So 0G means the absence of support forces. It means free fall, a spacecraft following an unconstrained track through space. In Skylab, it was much easier to appreciate the meaning of the basic principles which we now call Newton's laws.
My first law states that a body remains at rest or moves with constant velocity unless acted upon by a net external force. My second law states that the acceleration of a body is proportional to the net force exerted on it.
We found it quite easy to move equipment which would have been far too heavy for one man to handle on the ground. This gave us a real feeling for the way in which inertial mass resists the application of force. Inertial mass is the constant of proportionality in Newton's second law.
My third law states when a body exerts a force on a second body, an equal and opposite force is exerted by the second body on the first.
Here Alan Bean is exerting a force on the walls of Skylab, which produces a noticeable shaking of the image through one of our solar telescopes. The wall exerts an equal and opposite force on him. Small thrusters in this astronaut maneuvering unit exert forces on the gas particles which they expel. The motion of the unit results from the equal and opposite forces exerted by the gas particles on the thrusters. In the zero-gravity environment, we could demonstrate many phenomena impossible to see on Earth, some with important practical applications, such as growing semiconductor crystals. The effects you see here are strongly influenced by surface tension forces. On Earth, these forces are overpowered by gravity.
Zero-G continues, of course, outside the spacecraft during spacewalks, which are called EVAs, or extravehicular activity in the parlance of space talk. During the upcoming film clips, we'll see an animation of a spacewalk, or EVA, and an actual spacewalk. A neutral buoyancy facility, a big pool of water where spacewalks are practiced, is seen next. And then we'll see a Buck Rogers-like flying unit being tested aboard the Skylab space station. Finally, we'll see how astronauts can be rescued in a ball-shaped device.
EVA, extravehicular activity. All activities performed by the astronaut outside the pressurized spacecraft. For the United States, it began on June 3, 1965, when Gemini 4 astronaut Edward White became the first American to walk in space. The initial steps in the development of extravehicular activity occurred during the Gemini program. During Apollo, EVA was essential for setting up experiments, for taking lunar samples, for efficiently traversing and exploring the moon, not in the zero gravity of spaceflight, but in the 1/6 Earth gravity of an alien world. The ability to work outside the spacecraft became standard operating procedure. In later Apollo flights between the Earth and the moon, astronauts stepped into space to retrieve experiment packages. During Skylab, astronauts working in space were able to free a jammed solar panel that supplied electrical power for America's first space station. EVA was conducted throughout Skylab on a regular basis for operating experiments, retrieving film magazines, performing a wide variety of tasks. The techniques of EVA have allowed us to extend human capabilities in space. As standard operating procedure for space shuttle missions, EVA will increase efficiency and decrease the cost of servicing payloads, provide for on-orbit maintenance and repair of satellites, other payloads, and of the orbiter itself. EVA will meet various on-orbit contingency or emergency situations, such as freeing jammed mechanisms, providing significant assurance of a successful and safe flight. Shuttle EVA is patterned on past missions, Mercury, Gemini, and Apollo. While engaged in shuttle EVA, the astronaut will breathe pure oxygen. The EVA crew will acclimate their bodies by breathing pure oxygen from a portable oxygen system for 3 to 3.5 hours before EVA. To protect the human body from temperature extremes and from the vacuum of space, a special suit with a portable life support system is worn. It is called the extravehicular mobility unit. Under the suit, the astronaut wears a liquid cooling and ventilating garment to control temperatures created by solar radiation and by body heat. The extravehicular mobility unit is in 2 sections, making it easier to get into than suits used in Apollo and Skylab. First, the astronaut steps into the lower torso assembly, constructed primarily of flexible material. Next on is the hard upper torso assembly. The torso is built of fiberglass with flexible arm units attached. Then the connection to the liquid cooling and ventilating garment is made. The waist joint creates a pressure seal. Next on is the communications carrier and gloves. A helmet visor to protect the eyes goes on last. Then the astronaut begins breathing suit oxygen. The shuttle EVA suit is much more flexible in the joints and easier to work in than previous suits. Attached to the hard upper torso is the portable life support system, a backpack providing oxygen for breathing and for maintaining suit pressure, 4 pounds per square inch. A backup emergency oxygen supply is included. The backpack also provides chilled water for cooling and radio communications with the orbiter and other EVA astronauts. To see how EVA will work, we will present scenes from training exercises in the large water tank known as the Water Immersion Facility. The tank contains mock-ups of structures on which work will be done. The astronaut is weighted and balanced to achieve neutral buoyancy. This is an approximation of the weightless condition in space. A network of handrails and slide wires mounted in the payload bay assists the astronaut in moving from place to place. To provide illumination in the payload bay, there are 7 floodlights. Once in the bay, the EVA crew can do a number of tasks: inspection of payloads, photography, cargo transfer, scientific experiments, preparation of payloads. A storage area is located in the forward right-hand side of the payload bay, holding most of the tools needed for EVA. There are 3 types of EVA. Planned EVA, a part of the normal events to complete mission objectives, such as deploying experiments. Unplanned EVA, to correct problems and assure mission success, such as freeing a jammed power panel on a payload. And contingency EVA, to perform emergency tasks that will allow the crew to return to Earth safely, such as repairing payload bay doors before re-entry. In this contingency EVA exercise, astronaut John Young, commander of the first shuttle orbital flight test, is using a manual backup method to close the payload bay doors. These doors must be closed and latched before the orbiter can re-enter the atmosphere. Other EVA contingencies might include clearing jammed mechanisms or manually repairing and fastening payload bay door latches. In this underwater EVA, the crew is working on a mock-up of the 100-inch orbiting telescope. This telescope will be left in orbit and revisited by the shuttle on a regular basis. It will be retrieved by the shuttle manipulator arm and placed in the payload bay for maintenance and normal servicing. For some EVAs, the crew will leave the payload bay and venture into space outside the orbiter. To provide controlled movement from point to point, a special piece of equipment will be used. This is the manned maneuvering unit, a backpack using controlled jets of cold gas to let the wearer move from place to place. A prototype of the shuttle unit was tested aboard Skylab in the large workshop section. On shuttle flights, it will be carried in the payload bay. The EVA astronaut will enter the bay, step back into the unit, close and lock the latches, and release the flying unit from its mounting. he or she is free to move out of the payload bay to fly around the orbiter and perform a number of tasks. EVA, extravehicular activity, begun in Gemini, used for essential jobs, and developed in Apollo and Skylab. It's spectacular, and it's beautiful, but most important, it's an integral part of operational missions of the Space Shuttle, providing a wide range of services to the orbiter, to the payloads, and to photography and experiments. EVA will allow the fullest use of an ever more important aspect of space flight, the human factor.
During this program, we've seen a number of film clips showing spacesuits and how they work and the effects of weightlessness on man. What does all this mean to us in our quest to live in space and look for other life there? Well, man can work and live in the hostile environment of space and weightlessness. This means, among other things, that man will be able to eventually build large space structures for prolonged space use, including the search for life. This is Lynn Bondurant, hoping you'll join us next time to see Project Mercury, an early step into space.